All right, everybody, this is the third gas law. This is Gay-Lussac's law, and he is French, and his is Monsieur Gay-Lussac, and it's very lovely to talk in the fake French accent when you are talking about this law. I promise I will stop. I have a really bad fake French accent. I can't do that well, and when I have gone to France, people have made fun of me for it, and they're like, "Please stop. Just speak English like normal." So, yeah. So with all of that, all right, Gay-Lussac's law is going to be when we have a constant volume, and this is something that we haven't seen before. So what this is this is going to be a rigid container, something that doesn't change, like a marshmallow or a balloon or a syringe. So this would be like one of those rigid tanks, an aerosol can. So this is something that we would see with that type of situation. So at a constant volume, the pressure of a gas is directly proportional to temperature. If you looked at the Charles' law example, you would have seen that if we are directly proportional, that means that we divide our two variables in order to get our constant. So pressure divided by temperature gives me my constant K. K for constant, maybe it's a Kardashian influence, who knows, but that is going to show that if the pressure is going to go up, the temperature goes up, and vice versa. If the temperature goes down, the pressure goes down. So this is visible in the Gay-Lussac's law equation, P1 over T1 equals P2 over T2. And just like we saw with Charles' law, people like to cross multiply it out and write P1 over P1 times T2 equals P2 times T1. Definitely a tongue twister. But be careful here, okay? The ones and the twos, if you have the cross multiplied version, needs to do the 1, 2, 2, 1. Whereas if you are using the directly proportional relationship, you see that the ones and the twos are both on the same side in order to represent the before and the after in the experiment. So, very important that you pay attention to this because this is why it says on all of our aerosol cans, do not incinerate, which means don't put it in fire, even if it is empty. It is not empty. Okay, there's still a teensy tiny little bit of gas remains. The pressure inside the container equals the pressure outside, which is why nothing comes out. So that means that there is still gas in there. If you put it into a fire, temperature goes up, then the pressure will go up, and then you will see it explode. And we don't want that to happen. That could be very dangerous because we cannot predict which way the explosion is going to land, and it could definitely potentially hurt people. So, important things to remember with Gay-Lussac's law. It is a directly proportional relationship. So, pressure over temperature is our constant K. Okay, you divide both of them in order to get our directly proportional relationship. So, if you have two pressures, they must be in the same unit. Again, pressure is 1 atmosphere and 760 torr and 760 mmHg, millimeters of mercury, and 101.3 kPa. Important that you know how to convert all of those. And since we have our temperatures in the denominator again, they must be in Kelvin. No zeros. You cannot divide by zero. It will be undefined. So if you are given your temperatures in Celsius, you add 273 and then you get your Kelvin temperatures. It can't go through zero, it can't be zero, it won't work out for you, and you'll get very frustrated. That is possibly the most common mistake that I see with any of the gas law problems in my multiple years of teaching, is that kids don't change every temperature unit to Kelvin. Regardless of what it is, change it to Kelvin. All right, so examples of this obviously are the do not incinerate. We don't want that to happen. Okay, this over here is a canister, which if you see it in real life, it is about a 5 foot tall canister, and a company called Air Liquide, if it's pronounced correctly in the French accent. Okay, Air Liquide, they fill it with liquid nitrogen, which is at negative 195 degrees Celsius, very, very cold. It should be filled about halfway. This particular canister was being worked on right before spring break, and the operator that was filling it filled it twice. So they didn't fill it halfway, they filled it almost the full way. And when it's filled and then went outside, the temperature rose. So the pressure rose. And what happened is that this canister completely ripped, and it is like a fortified cast iron, and it ripped in half, and it was kind of launched across their campus. And because this happened like right before spring break, I guess their mind was on, oh, they're so happy to go home for vacation with their family. They didn't pay attention that they filled it twice, and the pressure was so great it launched it across campus, went through a different building. Luckily, since it was spring break, everybody was safe. Yay! But it is definitely dangerous. Okay, another video that I post on my notes that's embedded is from the Psy Guys, and this is Gay-Lussac's law in real life. So we've all seen the little dish that has water in it, and somebody puts a candle in it, and they light the candle, happy birthday to you, and then they take a beaker or a glass and they put it over top, and then it snuffs out the flame, so the temperature goes down. And then what happens to the pressure? The pressure goes down. Well, if the atmospheric pressure in here lower, or if the pressure of the gas inside lowers, the atmospheric pressure is going to push down on the liquid in great amounts, and it is going to raise the water level inside the jar. So you'll see right here they color it with blue, but basically as soon as the candles go out, you're going to see it pull all of your water in there. And then my chemistry teacher, oh, I love Mr. Ray. He's the reason I am a chemistry teacher. Mr. Ray is famous for telling his story about Leroy, which is a janitor at West Virginia University when he was getting his master's. And somebody had taken one of the tanks that they were using for their gases and wrote empty on it. Leroy interpreted that to mean trash. And what did they do with trash? They put it in the incinerator. Uh-oh. That is right. Well, the incinerator got really hot. It melted the connections right here where the brass meets the fortified tank, and basically this broke off and it started to shoot out the pressure of the air inside, because remember, it is not actually empty. Okay. And that was definitely something bad. So it went through walls, and everybody shook their head at Leroy, and Leroy didn't know any better, unfortunately. Okay, so let's try a sample gas law problem. All right, the pressure of a gas is changed from 1.5 atmospheres to 2.7 atmospheres of pressure. The resulting temperature is 425 Kelvin. What was the original temperature of the gas here? So now we're looking for what the O-ridge was. So be very careful when you read these problems. Sometimes you're not always solving for P2 or T2 or V2. You might be asked for the first initial one, P1, V1, or T1. So read the question carefully. Use context clues. 1.5 atmospheres is going to be from where it started, so this is going to be P1, to 2.7 atmospheres. This is P2. The resulting temperature, so that is T2 over here, is 423. The original temperature is T1, and that is unknown. So I have P1, T1, P2, T2. So P1 is going to be 1.50 atmospheres. P2 is 2.7 atmospheres. T1 is unknown, and our T2 is 423 Kelvin. Okay, so before you solve anything, try to predict what's going to happen. Okay, so my pressure went from 1.5 to 2.7. That means that it increased in pressure. So this is directly proportional, so what should happen to the temperature? The temperature should also go up. But we're not looking for the resulting temperature, we're looking for the average temperature. So that means you should see something lower than 423 Kelvin. So let's plug this in and see if we get a number that is indeed smaller. P1 over T1 equals P2 over T2. And we're going to plug this in. Okay, 1.50 atmospheres over T1 equals 2.70 atmospheres over, let's write this correctly, 423 Kelvin. Okay, so again, how do we isolate something that is in the denominator or a fraction? You can cross multiply and divide. That's why some people like to plug in the variables or the values into the variables when they're already cross multiplied. So that's P1 times T2 equals P2 times T1. But be very careful. You don't want to fall into the trap of the ones and twos because this is not going to be the same relationship as your Boyle's law. So when you do this, okay, you get 1.50 atmospheres times 423 Kelvin equals 2.70 atmospheres times T1. Now, how do I get T1 by itself? It is being multiplied by 2.70, so I got to do the opposite. Divide by 2.70 atmospheres. It's an equality. Whatever I do to one side, I do to the other side. Those two things cancel out, and I get my T1 on the left side. Atmospheres and atmospheres cancel out, leaving the units of Kelvin, which is a temperature unit I want. So how do I put this in the calculator? Go grab your calculator. Push pause if you need to. Okay, what you put in your calculator is every number on the top you multiply. If it's in the denominator, you divide. 1.50 times 423 divided by 2.70 equals, and we get a value of 235 Kelvin. Does my answer make sense? Did I predict a number that is indeed lower than 423 Kelvin? Why, yes. Yes, I did. So if the pressure changes from 1.5 to 2.70, the temperature will change from 2.35 Kelvin to 423 Kelvin. Okay, those of you that have my notes, you see them all laid out in the next couple of slides, and you end up getting 235 Kelvin. Okay, another really useful thing here is to remember how to associate the names of the scientists with their laws. I find this a little bit sexist, but sometimes it helps people. I want you to know that I know that boys and girls can both play volleyball, and girls and boys can both play tennis, but this is how some people remember it. I'll show you some other ways as well. Okay, so Boyle's law is boys play volleyball, P's and V's. Girls play tennis, P's and T's, and all children get very tired. Let's hope.